Okay, so the second problem that I'm going to solve is problem 8 in the practice problems. But before we get started on that, I just want to make one correction. When you look at the solution to problem 4, I said in the video that the magnitude of UBC, the position or the unit vector for the cable tension TBC is equal to 7. Actually, it's equal to 14. Okay, so when you do the arithmetic, you're gonna get the results to get the same answers that I had. All right, I just mistakenly said it was 7. All right, that the magnitude of the position vector RBC was 7. It's actually 14. Okay, so let's get to solving problem 8. So we read this, and what we see is the following: got a horizontal boom, ABC. All right, it's supported by a ball and socket at A, by 2 cables, one cable CE and one cable BCD or BDC, all right, that runs over a pulley at D, okay? So that's the situation. And then there's a crate, some type of an object hanging vertically downward at C that weighs 80 pounds, all right? Okay, so the question then says, determine the forces in cables BDC and CE. Okay, again, there's a single cable tension in BDC, all right, that's running over the pulley. So that's one cable tension that's being asked for, BDC, and the other is the tension in cable CE, and then last but not least, the reactions at A. So first thing we do, as always, we draw the free body diagram. So let me do that here. I'm not going to put the dimensions on here. Okay, of course, you have to have the dimensions on for a complete free body diagram. So here is the weight vector. Okay, at C, I have TCD. Okay, acting there. Here's B. I have TBD. Okay, that's the vector. And then I have TCE. Acting like that. So there's my free body diagram. And again, axes, this is Z, this is X, and this is Y. Okay, Y is along the boom, Z is vertically upward, and X, then if I consider the XZ plane to be a wall, there's anchor points at E and D. All right, so there's my free body diagram. Now, a couple things to note. All right, that the magnitude of the tension TBD is equal to the magnitude of the tension TCD. Again, it's a single cable running over a pulley. Okay, so the magnitudes are the same. Magnitudes are the same. Okay, so I look at this and I say, well, all right, I'm missing something on my free body diagram. I'm missing the reactions at A. So a ball and socket, if you recall, a ball and socket prevents translation in the X, Y, and Z directions. So I have an AY, an AZ, and an AX. Okay, so there's the 3 components of the reaction force. The ball and socket does not prevent rotation, so there is no reaction moment. There is no reaction moment, okay? So my reactions, the reaction force at A then is just AXI plus AYJ plus AZK. Okay, so there's the reaction force at A. All right. And so what I like to do first, and I did this in the solution to problem 4 as well. I like to do this first. I write the vector equations, the vector equilibrium equations first. All right, so what that tells me then is that A, the reaction force, plus the weight, okay, of that crate, plus TBD, plus TCD, plus TCE is equal to 0. All right, so I've got that first. Now I look at this and I say, before I jump into the x equation, I think it's typically kind of people think, well, I'll just do the x equation first and then do the moment equation. But it's the reason I do this, the reason I like to do this is for the following. I look at A. A has got, again, this is a Cartesian vector, so there's three unknowns here. AX, AY, and AZ. So there's three unknowns here. The weight I know, that's not an unknown. There's an unknown here. There's an unknown here, the magnitude TBD, the magnitude TCD. But again, since that is a single cable running over a pulley, the magnitude TBD is the same as the magnitude of TCD. All right, so that's one unknown. Okay, and then finally, I have TCE, the magnitude of TCE. So there's one unknown here. This is one unknown, and this is three. All right, so there's a total of five. Total of five unknowns in the vector sum of the forces is equal to 0. Right? As you know, there's only three equations of equilibrium. You might start with this and might get some of them. Maybe, maybe not, but you know you can't get them all with five unknowns and only three equations. So before you jump into the force equation, right, I think it's good then to write the moment equation. So that's what I'm going to do. Okay. Again, you can sum the moments anywhere. All right, so I have the vector sum of the moments about A is equal to 0. There's a moment about A due to the weight of the crate. There's a moment about A due to TCD, to TBD, and to TCE. So there's going to be 1, 2, 3, 4 components, 4 terms, I should say, 4 terms in that equation. Okay, so what I have then is, again, the cross products. I always use the cross product, so it's RAB cross TBD. That's one. That's the moment about A caused by TBD. I have RAC cross TAC. Okay, that's the second term. I have plus RAE, or RAC, I use C, sorry. RAC, again, it makes no difference, cross TCE. Okay, as you're well aware, when I'm doing the cross product, for the moment, it's the position vector from A, from where I'm summing the moments about, to any point along the line of action of the force. So RAC cross TCE, RAE cross TCE, or any position vector, any point along the line of action of CE. Okay, so you don't have to choose these three position vectors, RAB, RAC, and RAC that I chose. As long as it's on the line of action, makes no difference. And then finally, I have RAC cross W is equal to 0. Okay. All right, so again, I look at this. There's an unknown here, TBD. All right, there's an unknown. This should be, it's RAC cross TCD. Sorry, this should be CD. Okay. TBD, TCD, again, the magnitude of these two. All right, the magnitude of TBD, magnitude of TCD is TBCD, if I want to call it that, all right? That's one unknown right there, okay? And then I have TCE, okay? So this is what I've got, okay? So there's one unknown, TBD, TCD, TCE, okay? But again, the magnitudes of these two are the same, okay? Of TBD and TCD, they're the same, okay? So then these are my 4 terms in the moment equation, right? So when I solve these, what I'm going to get is, I'm going to get TBD, which is equal to TCD. I'm going to get these two, or 1, I should say, and I'm going to get TCE. Okay, so this is what we got. And then once I have the magnitude of TBCD and the magnitude of CE, I go back down to my force equation. I have this one from the moment equation. I have this one from the moment equation. And that then allows me to get AX, AY, and AZ. All right. So again, in this case, there's 2 unknowns here, right, in my moment equation, and there's all 5 of the unknowns right there. Okay. So that's why I think it's good to write these first before you start jumping into the equations, because I think the tendency always is to do the force equation first and then do the moment equation. In this case, clearly, you do the moment equation first, and then you return to the force equation. Okay? All right, so let's go to the moment equation. All right, so what I have then is this. All right, go back here. What I need is RAB and TBD, TCD, TCE, and the position vectors. All right, so I need TBD, TCD, and TCE expressed as Cartesian vectors. So that's the first thing I'm going to do. Okay, so do this first. TBD, piece of paper here. TBD. All right, the cable tension TBD is a vector, is TBD UBD. Right, and again, the direction of the cable tension TBD is the same as the direction of the position vector from B to D. So this is TBD, RBD over its magnitude. Okay, so this then would be minus 3I using the coordinates, minus 4J, plus 4K. All right, so there's the position vector RBD, and then I divide that by the magnitude, 3 squared plus 4 squared plus 4 squared to the 1/2. All right, so what then this gives me then is TBD is TBD. And its unit vector then is minus 0.468I. Right, minus 0.624J plus 0.624K. Okay. So TBD, here's the unknown, the magnitude TBD. Okay, so I have that. Okay. Getting the other two, TCD is equal to TCD UCD, which is TCD RCD, position vector divided by its magnitude. All right, may as well do this. TCD, okay, minus 3I minus 12J plus 4K. Magnitude 3 squared plus 12 squared plus 4 squared to the 1/2. All right, so in parentheses, I have the unit vector then. So this is TCD then is equal to its magnitude, TCD, and its unit vector, when you do the arithmetic, it's minus 0.231I. Okay. Minus 0.923J, okay, plus 0.308K, okay? So the unknown here in this, in the vector TCD is the magnitude TCD. But again, this magnitude TCD is equal to the magnitude TBD. So I could probably just write this as TBCD or something like that, okay? And finally, TCE. Again, TCE is equal to its magnitude times UCE, which is equal to TCE RCE over RCE. Again, the direction, which is TCE 3I minus 12J plus 6K. This is where having the coordinates come in handy rather than always having to refer back to the diagram. 3 squared plus 12 squared plus 6 squared to the 1/2. Okay, so TCE, so Cartesian vector then is TCE times its unit vector, which is 0.218I right? Minus 0.873J, okay, plus 0.437K, okay? So now I've got, go back to this, okay? Now I've got TBD, TCD, TCE expressed as Cartesian vectors, and now I can do these cross products. All right, so this is what we got. Okay, keep in mind, there's only two unknowns here. The magnitude TCE, which is right there, and then the magnitude TCD, TBD, which are equal. Okay, so there's only two unknowns here. So RAB cross TBD, is equal to TBD. You can pull that out, right? That scalar quantity, the magnitude TBD, IJK, all right? RAB, or this is RAB is 040, all right? Back to this just to show that, right? Position vector from A to B is just 4J, okay? And then TBD, minus 0.468, minus 0.624, and 0.624, okay? Okay, now, here, there it is, okay. Now TBD, you could have the components of TBD are minus 0.468 TBD, minus 0.624 TBD, and plus 0.624 TBD. So you could put TBD in each one of the terms in this third row if you wanted to, but I find it more convenient to just pull that out and put it right there. And so all I have then in my determinant is our numbers, okay? It's up to you how you want to handle it, doesn't matter, okay? Okay, do the expansion. What I get then, that this is equal to TBD times 2.496I, okay, plus 1.872K. No Y term, which makes sense, because again, TBD is going to tend to cause a rotation about the x-axis and the z-axis, but not about the y-axis. So it makes sense that there's no Y term in this equation. So there's RAB cross TBD. All right, that's one of the four that I need. Moving on, I get RAC cross TCD. Okay, again, I'm pulling TCD out of the determinant. You could leave it in the third row if you wanted to. Makes no difference. IJK. And of course, you could do 3 2x2s if that's how you learned it when you do the determinants. And then minus 0.231, minus 0.923, and 0.308. Again, just like I said previously, you could leave TCD in each one of these terms, or you could pull it out like I did there. All right. Anyway, when you do this, this is TCD. All right, when you do the expansion, 3.696 I, all right, minus or plus 2.772 K. Again, no Y component, no tendency for rotation about the Y axis, which makes sense. Number 3, okay, the moment caused by TCE. All right, again, I'm pulling TCE out. All right, RAC is 0.12, and again, make sure you do R cross F and not F cross R. And this is 0.218 minus 0.873, and 0.437. All right. Do the expansion. This comes out to be TCE, right? The magnitude times 5.244I. Okay, minus 2.616. K, again, no J term. All right. 3 of the 4 that I need. The last one is the moment about A due to that crate, due to that 80-pound crate. All right. So RAC cross W, IJK, 0, 12, 0, and 0, 0 minus 80. And then this is equal then to 960 minus 960 I. Okay. So now I got all 4 of the cross products that I need. Okay, go back to my first page here. So RAB cross TBD, got it. RAC cross TCD, got it. RAC cross TCE, got it. RAC cross W, got it. So I have everything that I need for the vector sum of the moments about A. All right. Okay, so now all I have to do is collect the I, J, and K terms. Okay, and so while I do that, I may as well do this. TCD and TBD, okay. TCD and TBD, the magnitudes are the same. So I'm just going to call that TBCD. All right, so now I collect the terms. All right, so sigma MAX, collect the X and Y and Z terms. So sigma MAX, the X components of the moments about A. All right, this is 0.2496 TBCD. Okay, plus, let's see, plus 3.696 TBCD, plus 5 points. Double check something here. I'm sorry, this should be 2.496. I got that wrong. 2.496 TBCD plus 3.696 TBCD plus 5.244 TCE minus 960 equals 0. Again, 2.496, 3.696, 5.244. All right. So this then is 6.192 TBCD, all right, plus 5.244 TCE minus 960 is equal to 0. Okay, so there is the X component of the reaction, of the, not the reaction moment, the moment about A. I do that same for Y and Z, MAY. Well, there is no moment about A, tendency for rotation about the y-axis caused by any one of the forces. So this is just 0, all right? And so finally, MAZ, I collect the Z components, all right? So it's 1.872 TBCD, okay, plus 2.772 TBCD, minus 2.616 TCE is equal to 0. All right, do the arithmetic. 1.872 plus 2.772 is 4.644 TBCD, right? Minus 2.616 TCE is equal to 0. Okay. All right, so I have my sigma MAX, sigma MAZ, two equations, two unknowns, the unknowns being the magnitudes TBCD and the magnitude TCE. Solving these, I get TBCD is 61.9 pounds, okay, and TCE is 109.9 pounds, okay. These values might be a little bit different from on the answer sheet, they're just rounding. Okay, that's all there is to it. All right, so now what I've got here is I've got the magnitudes of TBD, TCD, which is just TBCD, and the magnitude TCE. Okay, so now I can go back to my force equation. All right, I still have three unknowns, AX, AY, and AZ for the reaction force. I know the magnitude TBD, the magnitude TCD, and the magnitude TC, and again, the magnitude TBD is the same as the magnitude TCD, okay? So now all I have to do then, before I can collect the terms, the X and Y and the Z terms for the force equation, I need to express these tensions, TBD and TCD, as Cartesian vectors. So that's the next step, okay? I have the unit vectors. Right, so for example, here's the unit vector of TBD, here's the unit vector of TCD, here's the unit vector of TCE. All right, so in order to, and I have solved for the magnitudes, TCE, TCD, and TBD. So now all I have to do is multiply the magnitudes by the unit vectors, and I can get, and I need TBD, TCD, and TCE expressed as Cartesian vectors. So this comes out to be minus 28.97 I minus 38.63 J plus 38.63 K. Okay, so there's TBD, TCD, same thing, is minus 14, just multiply the unit vector by the magnitude, which is 61.9 pounds, so 14.30 I minus 57.13 J plus 19.07 K, okay, and then finally TCE, right, TCE 109.9 times its unit vector, so this is 23.96, okay, minus 95.94 J plus 48.03 K, okay, and then last I need the weight vector, which is minus 80K. All right, so now I've got all of the forces expressed as Cartesian vectors, and then again in my force equation, vector sum of the forces is equal to 0. Okay, that's just AXI plus AYJ plus AZK. Okay, and again, I always assume that the components are in the positive direction so that the arithmetic sign for each one of these terms is positive. Okay. All right, so I have what I need. Now I can turn my attention to the solution. Here in a second. Just 1 second. Okay, so I have all of the forces, right, expressed as Cartesian vectors, and my vector sum of the forces is equal to 0. So now all I have to do is collect the X, Y, and Z terms. All right, sigma Fx is equal to 0. Okay, so I have AX. Again, I've assumed it's in the positive direction, minus 28.97 minus 14.30 plus 23.96. All right. Again, these are scalar equations. So a little bit of arithmetic tells me AX is equal to, not minus, is equal to 19.31 pounds. Again, don't forget the units. Okay. Sigma Fy is equal to 0. So I have AY minus 38.63 minus 57.17 minus 95.94 equals 0. So AY comes out to be 191.7 pounds. Okay, there's the second one. And finally, sigma FZ is equal to 0. So I've got AZ plus 38.63 plus 19.07 plus 48.03. Okay, and then I have the weight minus 80 is equal to 0. So I get AZ is minus 25.73 pounds. Again, these might be a little bit different from on the answer sheet, which is do round up. Okay, so that solves the problem. It solves the problem. Because the problem asked for the reactions at A, at the support. All right, the reactions are a reaction force, no reaction moment. So I have three components, AX, AY, and AZ, and the tensions in the cable. All right, again, BCD, since it's run over a pulley, is a single tension. Okay, so that's the fourth unknown, and then the fifth unknown is TCE. The reason we have this, the reason I solve this, again, I think it's always good. It's my opinion. You don't have to do this. I always will do this first. I'll write the vector equilibrium equations first, and then take a look at them and see how many unknowns are in there. And again, for this problem, the vector sum of the forces, all 5 of the unknowns are in there. So before I jump into that, again, you might be able to get some of them. You know you can't get them all. The moment equation of sum of the moments are on A. There's only 2 unknowns there. Again, recognizing that the magnitude of TBD is the same as the magnitude of TCD. All right. So I say, all right, this is what I did. I solved the moment equation first. I get the magnitude of TBCD. And then once I have the magnitude of TBCD, then I can jump to the force equation and get the other unknown, because I already know what TCE is, of course. I know the magnitude of TBCD. I know the magnitude of TCE from the solution of the moment equation. Then I have 3 equations, 3 unknowns, and I get AX, AY, and AZ. Problem solved.